all the way to the back? Thank you. Yeah, I heard there was a prize for having the longest title. So for my talk, I picked a very long title. I'm honored and pleased to be here. Let me just start by talking a little bit about the last decade, which has really been the decade of accelerated computing development from our perspective. CUDA, the first programmable language that allowed general purpose GPUs to be used as computation accelerators, was introduced in 2006. And you can see we've had a very interesting experience growing into a high performance computing platform that's both very powerful and extremely efficient. And it's been very gratifying to have a number of science successes, as well as to find ourselves in the position of being able to offer very high performance and affordable, efficient computing for a new field that has just exploded in the last 4 or 5 years, using big data to train machine learning algorithms, most notably deep neural networks, using GPUs. Almost all the results that you've seen over the last 4 or 5 years that have been breakthrough results have been trained on NVIDIA GPUs. And so that's been a very interesting development for us. And part of what I'm going to talk about today is the interesting intersection between high performance computing and artificial intelligence. But I also promised in my abstract that I would talk about GPUs and the technology foundation and why there's a good reason to believe that GPU accelerated computing is going to be a very powerful factor going forward into the future, even with the fade of Moore's Law. So let's start with the top 500 list. Everyone has seen this. You can see the effect of Moore's Law over the last 20 years driving supercomputing almost in a straight line. The top line is all of the top 500 computers added together. The middle line is just the #1 system, so you can see it. Obviously, it steps up. And the bottom line is the number 500. And you can see that over time, a factor of 10 improvement has taken about the same amount of time each step to get to the next level of performance. But you can also notice that we should have been at an exaflop already by now. Somewhere around 2015 is when it should have been plotted on this chart. And it hasn't, partially because you can tell that there's something going on with the technology. And really, it's the beginning of the end of Moore's Law. And there's a number of effects that are taking place. And we can talk about those a little bit. This is a little longer time frame chart. This is 40 years of microprocessor trend data. You may have seen this chart. It's a really great illustration of both the power of Moore's Law during the first 30 years and also how it's starting to fade out. The top line is transistors. And what you'll notice first is that the number of transistors hasn't decreased. It's still following an upward trend, even though we're approaching the physical limits of our ability to make smaller transistors. But what you do see is right around the middle of the 2000s, early 2000s, you see that single thread performance, the blue line, starts to tip over. We're not seeing a single CPU is no longer able to improve that number at the same rate. Similarly, we see a limit to the frequency that we're clocking CPUs. And we also see that we're bumping up against the power limits that our server and desktop and even high performance computing packaging is configured to cool. And so what all of industry realized at that point of time, we're still getting more transistors, but we're not able to make good use of them in a single CPU. And so it's time to start spending those transistors not on trying to make a single CPU faster, but on multiple cores. So this period of time is really, this is now the beginning of the end for Moore's Law. And it's been going on since around 2003. Probably started slightly earlier than that. The largest factor in this is something called Dennard scaling. Over all of Moore's Law life, we have not only been increasing the density of the transistors on a chip, but we've been reducing voltage, cutting it and cutting it and cutting it. But transistors have a limit to how low you can drop the voltage before they won't work anymore because they have threshold voltages, and you need a certain delta V in order for that threshold voltage to make a transistor switch. But also, as you approach that minimum voltage level, you start to see transistor leakage become a higher and higher consumer of power. Ordinarily, during the earlier period of Moore's Law, when you cut the voltage, you gained a big power efficiency improvement as well as a larger number of transistors, and so you could use all of those transistors. But with the end of Dennard scaling, you still have the transistors, but now you may not be able to afford the power to be able to turn them all on. So the end of Dennard scaling is a bad thing and really at the core of the performance effects that we're seeing at the end of Moore's Law, even though we're still getting the transistors. So this chart shows that the conventional microprocessors in blue, and then starting in the middle of in 2006, these are GPUs added to that line. And GPUs are really, think of them as the ultimate multi-core, right? And their time arrived because a single core could no longer be made faster at a Moore's Law rate. You can see that we're continuing on average to drive the performance of GPU computing forward at about 1.5 times per year at something pretty close to the traditional Moore's Law rate, even though we have such nasty things as the end of Dennard scaling happening. So why is GPU accelerated computing so efficient? Why are we able to use all of the transistors? Why are we able to increase the performance even though we're approaching the physical end of our ability to make transistors smaller? So I'll talk about that. So this is a comparison between two contemporary devices. On the left, we have a Broadwell generation Intel CPU. And on the right, we have Pascal, which is a similar generation. They're contemporaries. And this is a measure of efficiency of computation. It's measured in picojoules per floating point operation. And the CPU is between 4 and 5 times less efficient than a GPU in terms of energy efficiency. Why is this? Well, architecturally, part of the reason is that they're just designed for different jobs. And part of the reason is their heritage, their roots. CPUs started out as being, taking a single serial step at a time. They would fetch data from memory, operate, and store the data back to memory all in a single cycle. And then they would do that again and again and again. And if you had a large array of data that you wanted to perform operations on, the same operation on it, you did it with loops. You sequentially stepped through the data and did it all serially. And so latency of operations, even as architectures progressed and we introduced pipelining and we started to introduce a number of additional architecture tricks to try to speed up that serial processing model. latency really became the big enemy. And so, deep and fast cache hierarchies were introduced, things like branch prediction and speculative execution, registry naming. All these techniques have made our ability to execute a single thread that has serial dependencies in it, just go faster and faster and faster, but at a cost. It takes transistors, it takes power to do all of that extra calculation associated with even deciding if you have the data ready and it's okay to do the computation. So, caches, very important, low latency, very important for that kind of compute model. GPUs are completely different. They have a heritage that comes from an embarrassingly parallel application, which is graphics processing and painting pixels, rendering polygons onto a screen. The screens have millions of pixels. We're rendering 60 or more frames per second. We have billions of polygons that we're going to determine the visibility and the color and the lighting and shadowing and all of that. And all of them can be processed completely independently. And so from the very start, graphics processors had a job that was completely parallel. And so there's really almost no concept of a loop. Instead, it was how many graphics cores can you put together and orchestrate with a multi-threaded model. And they started out to be hardwired pipelines, but then they became programmable, and then people started, NVIDIA most notably, started investing in both how to make them programmable and more easily programmed, hence CUDA, OpenACC, other models like that, but also how to make the cores more efficient and more generally usable on a wider set of algorithms. And so GPUs are optimized for throughput, and they're latency hiding devices. They're not low latency devices. The latencies that a GPU has to load data from memory is very long, much, much longer than a CPU. But we don't care because we're launching thousands and thousands of memory references at the same time, and the name of the game in throughput computing is to push data through the pipelines and completely saturate the pipelines. And so that's an entirely different design approach. And because of that, the cache hierarchies and a lot of the design constraints and design goals for conventional CPUs just don't apply for GPUs. And this is important to understand because you'll see then how this enables the GPU to be designed using techniques that really aren't applicable to CPUs. So one of these is to just use very simple cores. This is essentially, so this was a PhD paper from 2010, but it's just showing the different cores and the amount of energy that it takes per instruction as you start to go more and more you introduce more and more complications to the architecture in order to try to do more work with a conventional CPU architecture. So on the far left, we have in-order single-way issue, and then we start doing multi-way issue, then we get to out of order. And you can see that the power required per instruction, that's what's charted here, the per operation, the power per operation starts to go up exponentially as you start trying to do more and more things in order to be able to predict and shorten the latency and achieve a higher rate. If you plotted a GPU core on this, or a GPU, it would be somewhere over here. It'd be tens of thousands of equivalent MIPS or operations for only around 10 or so picojoules per op. And this is because GPUs have this multi-threaded architecture, and many threads that are all executing the same instruction are issued with a single instruction mechanism all at the same time. So it's far more efficient than even single-way issue in order execution. And we hide latency latency by just automatically going on to the next thread and the next thread and the next thread while a thread is waiting for the data to come back. So simpler cores, that's an important factor here. But it's only part of the answer, and there's actually danger to assuming that simple cores is the answer. And I can illustrate that danger by comparing a couple of computing models for accelerators. On the left, I have what I call many weak cores. Think of this as Xeon Phi, like Knight's Landing or Knight's Corner. And it's basically taking CPUs and making more simple versions of them using single-way issue or two-way issue, getting rid of the branch prediction or speculative execution, just simplifying them to the point where they're at an optimal point for efficiency. And you end up with weaker cores, but you can now replicate them and have lots of them. Knight's Landing had something like 72 cores on one chip. 72 atom cores. Each one was around a third or a quarter of the serial performance of a server class Xeon. On the right, I'm going to compare this with the accelerated computing model. The accelerated computing model has the benefit of having this wonderful parallel processor, this GPU, but it's also penalized by requiring a powerful CPU as the host. The GPU is an accelerator to the host CPU. But that's actually also a benefit because we can take a full power CPU that has the fastest serial processing capability in the world and use that to minimize Amdahls Law effects. And let me just compare then a couple of scenarios. So I needed to compare the same number of sockets, so we're talking about the same cost. So the top line here is a single GPU. Just assume this is just an analysis, but it holds true in real life. Imagine a single Pascal with a single Broadwell as its server class Broadwell as its host, and that's 2 sockets. So the next line down, I'm assuming we're going to use 2 Knight's Landings. And actually, that second line down has twice the peak performance of the top line, has twice the parallel peak performance of a GPU and a CPU. The bottom line is a measurement of the work. And so this is how long it would take to run an application that had, in this case, 98% of the work is parallel and 2% is serial. But that's basically a single Xeon core, a single thread. This is the baseline. This is the execution time for a single core. And you can see that there's an advantage to having the 2 many weak core devices. That factor of 2 higher peak performance gives somewhat better performance than the 2 sockets in the top line, the GPU and the CPU. But you can see the orange is the serial portion. You can see that already, because it's a weak core, the serial portion, even though it's only 2% of the work that needs to be done, is occupying twice or 4 times as much time as it takes for the single core in the bottom line, or the single core that's driving the GPU, that's hosting the GPU in the top line. And this is where things break down. And I don't think it's too early to say that the Xeon Phi architecture philosophy and Knight's Corner and Knight's Landing and the canceled Knight's Hill, I think, demonstrate that this philosophy is a failure. Part of the reason for this is because of Amdahls Law. And so you can see that when you drop to even just 90% parallel work, that already the serial fraction just makes it extremely difficult to realize the same kind of performance benefit in sustained performance that you have on paper with twice the peak performance. And things only get worse from there. And there's actually even a point at 70% parallel work where a single server-class Xeon core would outperform a pair of Knights Landings. And of course, things only get worse from here. The advantage of having this heterogeneous compute architecture where you have a powerful CPU hosting one or more powerful GPUs, the advantage of that is Amdahls Law resistance. And Amdahls Law is inescapable. So this was clearly one of the design flaws of the Xeon Phi architecture philosophy. And also, there have been other in the ARM space. Cavium has put together very large numbers of cores, and others have taken this approach of just using simple CPU cores to try to make an efficient HPC processor. And in my view, it's not a good idea. Another factor beyond Amdahl's Law, though, is the cost of communications and coherency in a multi-CPU, a many weak core kind of architecture.